Sound absorption is the effect on sound when it travels from one medium into another. For example, when sound goes from air into a solid medium like a wall, the solid medium absorbs some of the energy from the sound, resulting in a muffled or quieter sound on the other side of the medium. In my experiment, I tested how different factors affect sound absorption. My experiment had three problems. First, I wanted to test how different materials, such as cardboard, foam board, and wood, absorb sound. And my second problem, I wanted to test how sounds of different hertz levels, that is, sounds of different pitches, are affected by sound absorption. And my third problem, I wanted to test how the thickness of an insulator affects sound absorption. My hypotheses for the first part of the experiment with the different types of insulators was that wood would absorb more sound than cardboard, and cardboard would absorb more sound than foam board due to wood's greater density than the other two materials. My hypothesis for the second portion of the experiment with the hertz levels or pitches of the sounds was that a sound with a lower hertz level would be absorbed less than one with a higher hertz level. My hypothesis for the thickness of the sound insulator was that a thicker insulator would absorb more sound than a less insulator that wasn't as thick. For my basic procedure, we use a setup like we have here. And this setup has all of the factors held constant. It has a 2 centimeter thick cardboard insulator, which goes in front of the box with the speakers, like this, except it was taped on. And then an 1,000 hertz sound sample, which we got off of onlineToneGenerator.com. To do the experiment, we used this decibel meter, set distance away from the box, and then we set the decibel meter to record the highest given volume of sound, and then we played the 1,000 hertz sound sample. Sounds just like that. And then I'd record what the decibel meter shows for my result. In my first experiment with the different materials, we used a 1 centimeter thick insulator and 1,000 hertz as constants. For the variables, we used cardboard, foam board, and wood insulators. For my second experiment with the different hertz levels, we just used the 2 centimeters of cardboard, but we changed up the hertz level of the sound. We used 100 hertz, 1,000 hertz, and 10,000 hertz. 100 hertz sounds like this, if you can hear it. And 10,000 hertz sounds like this. For the final part of the experiment, we tried different thicknesses of the insulator. For this, we used just the 1,000 hertz sound sample, and then just one layer of cardboard, which was 5 centimeters thick, 2 layers, which is 10 centimeters thick, and 3 layers, which is 15 centimeters thick. For my results for the first portion of the experiment with the cardboard, the 10 centimeters thick of cardboard and 10,000 hertz, the sound averaged at 84.4 decibels with a minimum of 83.4 decibels and a maximum of 85.4. The sound going through the foam board averaged at 87.7 decibels with a minimum of 87.3 and a maximum of 88.2. The sound going through the wood insulator averaged at 82.0 decibels with a minimum of 81.3 and a maximum of 83.5. For the experiment with the different hertz levels and 10 centimeters thick cardboard insulator, the 100 hertz sound sample averaged at 69.8 decibels with a minimum of 69.7 and a maximum of 70.0. With the 1,000 hertz, the setup was the same as in the first experiment, with 2 layers of cardboard 10 centimeters thick and 1,000 hertz, so we used the same results, which were 84.4 decibels average, 83.4 decibels minimum, and 85.4 maximum. For the 10,000 hertz, the average was 30.8 decibels, with a minimum of 30.1 and a maximum of 31.8. For the different thicknesses, the one layer, or 5 centimeters of cardboard at 1000 hertz, averaged at 90.4 decibels, with a minimum of 89.4 and a maximum of 91.3. The 10 centimeters thick cardboard was again the same setup as in the other two experiments, so we used the same results: 84.4 decibels average, 83.4 minimum, and 85.4 maximum. For 3 layers, or 15 centimeters thick, the sound averaged at 84.2 decibels, with a minimum of 82.9 and a maximum of 85.7. In conclusion, my hypothesis with the different materials was supported. Due to its density, wood did absorb more than the other two insulators. With the hertz levels, my hypothesis was not supported. The 1000 hertz was absorbed the least, followed by the 100 hertz, followed by the 10,000 hertz. For the thicknesses of the insulator portion of the experiment, my hypothesis was supported. The thicker the insulator absorbed more sound. However, the difference between the 5 centimeter thick and the 10 centimeter thick insulator in absorption was far greater than the difference between the 10 centimeter thick and the 15 centimeter thick insulators. In fact, it was hard to tell the difference at all. In conclusion, through further experimentation, one could find out how to absorb sound most efficiently with the optimum materials. Any questions?
Yes, I have a question. So, it seems that with thicker and thicker, does it seem like that once you get to a certain thickness with an insulator, that the sound has just stopped? But of course, in your last experiment, you kept adding, if I understand it right, you kept adding the thickness of the thickness.
Yeah.
So you had a big response with the first edition of 5 centimeters, I think it was.
Yeah.
But then it got less. Then the next one was less. So what do you think happened there?
I'm not sure. In order to get it more accurate, you would have to keep testing to see if there's another large drop off at like 20 centimeters or 30 centimeters. But from what we've seen, the returns from 10 centimeters to 15 centimeters, there wasn't very much difference at all. But you'd have to experiment more to see.
It's kind of a non-linear thing. You get a certain response apparently, but then after that, you've already muffled it. It doesn't make much more difference.
How many repetitions did you do for each one?
For each setup, we did 10 repetitions. So that's 30 repetitions for each of the 3 variables in every experiment.
Thank you.